My name is Gamanez. I am from Pontlab. We are a testing lab. We are specialized in material analysis and testing on components. We are located in Tuscany, in Pontedera. It is between Pisa and Florence, and we have in our premises different instrumentation, and we perform typically material analysis. I mean physical and chemical characterization of materials, both metallic and non-metallic materials. We perform mechanical tests. This afternoon we will talk about fatigue test on materials. We can perform also durability and aging test on material and components. And we have also a specialization in metrology. We have also an industrial TAC, a tomography. And we perform also a lot of failure analysis. Our lab works in different sectors. We are specialized in materials, and for this reason we can address different sectors. Our main sectors, of course, are automotive and oil and gas. This afternoon we will show you a study that we have performed this winter in our lab, and we thought to make a study to understand how 3D printed materials which is the behavior of this kind of materials at fatigue test. As you know, the 3D printing in metals is a growing technology in these years. Of course, it is used when it is requested a complexity of the shape of the product. It helps to obtain some products in a very short time, and also has an advantage to make some object with the same functionality but with less weight. Of course, this new technology needs also a new way of thinking, and I mean it in the design. So now we can think the object in a different way from what we have done in the past, and also in testing. Here in this image, you will see the same type of material, that is an aluminium. On the right side is obtained by casting. In the left side by additive manufacturing. And you can see that there is a great difference in terms of the structure of the materials. And of course, this has also an influence on the mechanical behavior of the objects. We have performed this study, and now Matteo will show you the results. Thank you.
Hello to everybody. I'm Matteo Ferretti, and I will explain my thesis work that I carried out in Pontlab. My thesis work talk about the fatigue mechanic, the comparison of fatigue mechanic between the same type of aluminum, but produced by two different methods: selective laser melting and casting. The study is a fatigue crack growth test that is being carried out following the norm ASTM E647. The tests were conducted using an MTS machine landmark 2050, and the measurement of the crack length was conducted by a strain gauge with this model. The strain gauge, in particular, measures only the COD. COD is the crack opening displacement, is the distance between 2 points over the specimen. This means that the measurement of the length is indirect and depends on the mechanical characteristics of the material. The tested material is ALCI 10mg, that is a typical casting aluminum. And for this study, we used 6 specimens produced by continuous casting, identified with the code T, 6 specimens produced by selective laser melting, grown in the direction of thickness that colored horizontal and identified with the code O, and 6 specimens produced by selective laser melting, going in the direction of the load, colored vertical, identified with the code V. In addition, another 9 specimens were used for the tensile test, and 3 for each type. The tensile test is fundamental because a measure of the elastic modulus of the material is fundamental, because the COD needs the elastic modulus to measure the crack. The tensile test carried out with the same machine and gave the following results. And as we can see, the casting specimen have a slightly better mechanical characteristics. But more interesting is that between the 2 additive specimens, the horizontal specimen have the better mechanical characteristics. There is a difference as regards the building direction of the specimen. Generally, this type of aluminum has a fragile behavior. The FCG test have been carried out with these parameters: maximum load and amplitude of 2 kilonewton, load ratio, that is minimum load over maximum load of equal to 0.1 or 0.5, and a frequency of 4 Hz. The specimen that is like this in the picture is CT specimen, compact tension specimen, and the dimensions are the following: W of 40 millimeters, A0 of 14 millimeters. A0 is the initial notch for the crack, the cracking of the specimen, and a thickness B of equal to 8 millimeters. The test results is like this. A lot of points over a graph. In this graph, have in the ordinate the crack rate, the crack growth rate, and in the abscissa delta K. Delta K is a parameter for for fatigue stress, and it depends on the load and the length of the crack. In this raw data, we can see easily the linear part. In the linear part, that is also called the Paris zone, the data must be fitted to obtain the two parameters of Paris equation, C and M. And this graph is in logarithm scale. In fact, the Paris equation is an exponential equation. With the parameters C and M obtained from the test, it's possible to compare the different types of specimens. It's important to identify the load ratio effect. Load ratio move the curve to the right. The curve to the left is for load ratio equal to 0.5, and to the right is the load ratio equal to 0.1. In this picture, we can see the difference between the type of specimen. The casting specimen, identified with the T code, have a more inclined curve. And the additive specimen, horizontal or vertical, are between these two types is a big difference in fatigue behavior. The difference between the additive specimen is very interesting, and it demonstrates that the additive manufacturing, the final characteristics of the components depend on the production process, in particular on the building orientation. This difference was expected and is due to the microstructure of the material. In fact, the vertical specimens have the grain elongated perpendicular to the crack direction. The grain is a sort of barrier for crack, and in fact, the crack growth rate is lower. After this study, we carried out a porosity analysis. In fact, the presence of porosity is a big problem for additive manufacturing. And as we can see in the picture, between the two types of additive specimen, there are no difference. The porosity is similar. And instead, the porosity of the casting specimen is much lower. With both these test results, with the porosity test and the FCG test, it's possible to simulate a fatigue test to obtain the SN curve, stress and the number of cycles. The tests are simulated by the software AFGROW with a square section of 5 millimeters using a circular initial defect with a diameter equal to the maximum vacuum measured in the porosity test. In the table, we can see the maximum dimension for each type. The test gave the following SN curve, and this curve is for mid stress equal to 0, and in particular have a 99.87 survival rate and the 95 level of confidence, for which this level of reliability is the amplitude was reduced following the normal distribution. To verify the reliability of this method, of this curve, they have compared the SN curve obtained by the juvenile approximation. The juvenile approximation is a method to obtain the SN curve from the static mechanical characteristics, from the yield stress and the ultimate stress. The results are good, especially for the additive specimen. This means that this approach is correct, and obviously is necessary to confirm the curve with a real fatigue test, but it's possible to obtain an approximation of the fatigue of the ruler curve from a test of fatigue crack growth. The casting specimen have a too good behavior. This fact is caused from the dimension of the initial defect, that is too lower, and the model used by half-grow can't simulate the crack growth from a little defect. And now I'm approaching to the conclusion. The anisotropy of additive specimen cause a significant difference of mechanical characteristics between the horizontal and vertical specimen. This means that the production process has a not negligible effect on the final mechanical property. For these reasons, the design by additive manufacturing needs a change in design process. The production process, especially the building direction, becomes an integral part of the design process to obtain good results or results similar to casting components released by casting or another technology. Thank you for your attention. And